We would like to go through Module 3, Principle of Chemistry 1, or General Chemistry 1, Stoichiometry. This chapter here will cover first what is the definition, what is the mole. It turns out to be the mole is defined as the mass of a compound or element that contains the same number of fundamental units as there are atoms in 12 grams of the carbon-12 isotope. It means that in 1 mole, exactly in 1 mole here, let's put here, 1 mole of carbon here, we have, in 1 mole of carbon, we have exactly what 12 grams of carbon isotope 12. The word mole is introduced by a German chemist Wilhelm Ostwald in 1894, and this is really is abbreviation of a molecule. Molecule in German, so to say this molecule is mole, abbreviation of that. Furthermore, we will learn that 1 mole is equal the Avogadro's, and this is Avogadro number here, of particles. These particles can be atoms, can be molecules, or can be formula units or ions. An example here, just an example shows this is a carbon atom. It weighs 1.99625 10 to minus 23 grams. You multiply it by the Avogadro's number, and you get 12.0217 gram, which is really this value here is the atomic mass of isotope carbon-12. So this has to be the atomic mass of the carbon-12 isotope. And the number of Avogadro's number is here, 6.022 10 power 23. And here's the definition. In 1 mole, we have Avogadro's number of atoms or molecules or ions, or called sometimes formula units. Conversion of moles into grams for element, for example. So how we convert grams of an element into moles? Well, in this case, we will need to know the atomic mass of that element, which can be taken from the periodic table. So, and in the table, periodic tables, all this the atomic masses are average weight atomic masses, as you know, from the Survey of Chemistry 1. This is all the atomic masses in the periodic table are average weight atomic masses. So let's calculate. We have 10.5 moles of helium, and we want to get this moles converted into to get this moles converted into grams. So we'll start with the moles. This is given to us, and then we have to. This is the atomic mass of helium, correct? Helium, He. And if you can see, always look at cancellation of the units. So here it is. The unit is moles, with the moles cancels out, and this is the answer. Is this the final answer? The answer is no. We have to look at the sig fix. So we have here sig fix 3, correct? 3 sig fix. 3 sig fix, and therefore our answer has to have what? 3 significant figure as well. Now, another example here, how to convert moles into grams. That's the opposite part. So going from moles, if I can go back here, going from moles into grams, we multiply by the atomic mass for the element, correct? Now, going for moles into grams, then you can see for the molecule, you have to include the molar mass, not the atomic mass. This time, you have to include the molar mass of that molecule or compound. So how many grams, this is asked, is given to us. We have 20.25 of sodium chloride. So the first thing is to get or calculate the molar mass of sodium chloride molecule. So the molar mass is defined as the sum of the average weight atomic masses of each atom involved in the compound. So we have to know we have sodium here and we have the chlorine atom. So we have to add the atomic masses of both, which is 23.0 gram per mole for sodium and 35.5 gram for chlorine atom. So you add them up, and this is the molar mass. Now the 2.5 moles that's given of sodium chloride molecule or compound, we multiply it by the molar mass, correct? Which is gram per mole. So you'll see nicely is the moles with the moles cancels out. And this is the key of solving those problems. Always watch for two things: the units cancellation and the significant figures. So we started here with the 4 sig fix, correct? Let's make it here 4 sig fix. So our answer has to have 22.25, correct? And when we add them up, then the molar mass came out to be 58.53. So our answer will have 3 significant figures. Okay, so we have to go this one here, move this one here to 3 significant figures. So now we want to look at how we can convert grams into number of particles, which can be atoms, molecules, or formula units, ions, correct? Well, we can do this, but the key point, we have to get into the middle here. We have to convert whatever grams we have into moles, and then from moles into atom molecule. How we do this? Well, it turns out to be the first step, transferring grams into number of particles. You have to divide by the molar mass for the molecule or by atomic mass for an element to get what? To get number of moles. That's what you get. Then you multiply, so divide, as I said, divide the first step by the molar mass and multiply here by the Avogadro's number to get the number of atom, molecules, or ions. Now you can see the answer is expected to be very high. From grams into number of atom, molecules, or ions, or formula units has to be very high. An example here, 10.00 grams of carbon, correct? I want to transfer to calculate this one. How much 10.00 gram of carbon, how many atoms does it contain? Well, it turns out to be, I have to divide it by the atomic mass, of carbon, correct? 12.0011 gram per mole. I get the moles here, that's the key. Multiply the moles by Avogadro's number, atoms per mole. The mole will cancel out with the mole, carbon, and I get a large number, as I said, of atoms of carbon, correct? And I have to observe, here's 4 sig fix, and here we have 4 sig fix. I have to watch the 4 sig fix for my final answer. Now, we can go the opposite. I can have, or I can be given number of atoms, molecules, or formula units, and I have to calculate the grams. So this one is just the opposite. Remember, when I went from gram to number of molecules, atoms, or formula units, I'm repeating myself, I have to divide by the molar mass or atomic mass and then multiply by Avogadro number, correct? Here is the opposite. I am given the atoms, molecules, and formula units or ions. I have to divide by the Avogadro's number to get the whole thing is to reach the moles. If I have the mole, then I have to multiply this time by the molar mass. So the moles with the moles cancels out. I get number of grams. Look at the example here. I have 5.04 10 power 23 atoms of carbon. Correct? I want to transfer it. How many is equal to grams? Well, I take it here. I divide it by the molar, by the Avogadro's number first. So Avogadro's number here, atoms carbon cancels nicely with atoms carbon. I get into the moles here of carbon. Then I have to multiply it by atomic mass of carbon, 12.011 gram per mole. The mole cancels out the mole, and then I get 10 grams. I can see this one here in this diagram. If I go from grams into number of atoms, molecules, or ions, or formula units, I have to go through this step. First, I have to divide by the molar mass or atomic mass, if that's an element. And then second step is to multiply by the Avogadro number. If I have to go from the number of molecules or atoms or ions, formula units, to number of grams, I have first divide by Avogadro's number. Second, I have to multiply by the molar mass for a molecular compound, or by atomic number if I have an element, if I consider an element. So let's do one of these examples here. And let's do this one here and say, convert 4.50 moles of iron into atoms of iron. So we are converting here. Maybe I'll just, the last one. Okay, so I'm converting this 0.4 moles, correct, into atoms. So I have moles into atoms. Do I need the atomic mass of iron, Fe? No, because I just take the moles, multiply it direct by the atom per mole Avogadro's number. You will see nicely the moles here cancels out with the moles, and here they cancel out, and I get number of what? Number of atoms of iron. Again, here I have to watch for what? Unit cancellation, moles with moles out of iron, and the sig fix. I have 3 sig fix given to me. I have my answer has to come up with 3 sig fix as well. Another example here, convert 0.45 grams of iron into atoms of iron. Well, now as the gram is given to you, and you get the number of atoms. And remember, number of grams is always smaller. Number of atoms, molecule, or ions will be large because of the fact you have to multiply it by Avogadro's number. So now I have the grams. I want to go to the atoms. I cannot get the number of atoms from the grams unless I have to go to use what? To use the moles. I have to go through the moles. So the first thing here, if you look, you need the atomic mass. You divide the grams as here, as in the top. Take the number of grams of iron. This is the first step here, correct? And then you have to divide it by, I'm dividing it by the atomic mass of iron. So the grams of iron cancels with the grams of iron out, correct? That's dividing. And then I multiply this one here by Avogadro's number, correct? Then the moles of iron with the moles of iron will be cancels out, and I get here my answer. And then I have to watch for sig fix. 3 sig fix the answer. Now another example. Let's convert 0.200 grams of H2O into molecules of H2O. Well, here is the same thing, but here we have H2O. Then I have to calculate the molar mass of H2O. So I have to go through the molar mass of H2O first to get the moles. From moles, then I can go further. So here it is, the H2O molar mass, 2 hydrogens, 1 oxygen, 2 multiplied by 1.00 gram per mole for hydrogen, and 1 oxygen, 1 multiplied by 16.0 gram per mole, that's atomic mass of oxygen. It adds up to 18. The molar mass of H2O is 18.0 gram per mole. Then I have the molar mass of H2O now. I take the number of grams of H2O, 0.200 grams, correct? Divided by, I have to divide it by the atomic, by the molar mass, sorry, by the molar mass, this is a molecule here, by the molar mass of H2O. So you will see by doing this, the grams of H2O with the grams of H2O cancels out. And then multiply the whole thing by the Avogadro's number. So that the moles here cancels out with the moles here, and then my answer is 6.68, 10, sorry, this is not there, 10 power 23, 10 power 23. Here it is at the bottom here. The bottom here is written. Okay. Another example, convert moles into molecules. I have these moles here. The question, do I need the molar mass? The answer is no. I don't need the molar mass of H2O this time. Why? Because if I have a mole, just multiply it, because Avogadro's number of molecules per mole, or atoms per mole, or ions per mole, formula units per mole. So just take this one here, multiply it by Avogadro's number. The mole H2O with the mole H2O cancels out. And this is your answer here, number of molecules of H2O. Again, here you have to observe the molar mass, the significant figure, no molar mass, sorry, the sig figs. We have 4 sig figs, and here's 4 sig figs. My answer has to have 4 sig figs as well. Next. Well, this question is, which contain more molecules? 10 grams of oxygen or 50 grams of iodine? Well, without even doing any calculation, you look at the molar mass of oxygen versus the molar mass of iodine. You set up the whole thing together and look at the values, and you can determine which will be greater, which will be lower number of molecules. Let's do that together. Number of oxygen molecules, I start the same thing with the number of given to me, 10 grams of oxygen. Then I have to divide it by the molar mass of oxygen, which is 32, two oxygens. Okay, and then multiply it by the Avogadro's number, correct? Here with the iodine, I do the same thing. I have iodine here is 50. But the molar mass, look at how huge, is really huge. It's about 8 times larger than the molar mass of oxygen molecule. So multiply by the Avogadro's number. So this is still the Avogadro's number, in both are the same, correct? 10 and 50 is not that big difference, but the difference in the molar mass will make a big difference. You divide in iodine the whole numbers by huge numbers, so you can expect small number will come out. So as I said, no need to do real calculations. Just inspect both equations. Iodine equations must be divided by the value of 253.8, which is almost 8 times larger than the value of the molar mass of oxygen, 32.0 gram per mole. And therefore, oxygen will have more molecules because you divide the whole thing by 32 different, but here you have to divide by 253, which will lower the value. Now let's look at this now here. Now I'm looking at the number of atoms within what? Within the molecule. Now I'm looking at what? Each individual atom within the molecule. If I have, and this is very interesting example, I have 18 gram of H2O is present. Asked is how many oxygen atoms present and how many hydrogen in H2O. We know that's 2 hydrogens and 1 oxygen, correct? That's the ratio between the atoms. But we need to know exact number, not 2-to-1 ratio, but we need to know if I have 18.5 grams, how many oxygen atoms are present in 18.0 grams of H2O, and how many hydrogens. So let's do this together. First of all, I have to convert the grams into moles, correct? 18.0 grams per mole, 18 grams. This is the sample of H2O given to me, divided by 18 molar gram per mole. That's the molar mass of H2O. I have 1 mole. So 18.0 of H2O grams equal 1 mole of H2O. Then I convert the moles into molecules. So I can do the whole these 3 steps in one step, but it's better to break it down so you can follow me. Convert the moles. I take the moles multiplied by the Avogadro's number. I get that much of molecules in 1 mole, correct, of the H2O. And that's really always true. That's the rule. In 1 mole, I have Avogadro's number of molecules of ions or ions, formula units. Now, the third one, which is this really very unique. This is very unique. This is new. This is new. So approach. I have this number of what? Of molecules present in one mole, of course, correct? These are the number of molecules, correct? And then I ask myself, how many oxygen atoms I have in this molecule? So it turns out to be I have 1 oxygen atom, 1, in 1 molecule of H2O. So the molecule cancels out with the molecule. So I get what? 6.02 Avogadro's number multiplied by 1. I get number of oxygen in H2O. And the same thing I do it for hydrogen. However, hydrogen we have 2 atoms in 1 molecule. So then I'll multiply the molecules, cancels out with the molecules. I get this one here to be, I have 1.2010 power 24 hydrogen atoms in 1 mole of H2O. So now let's look at an example here. If I have a molecule, and I have to calculate as here how many carbon atoms does the sample contain. A sample of C3H8 has, this is the number of atoms in this molecule. It does not give us any grams. The grams are not present. The moles are not present. Present to me is C3H8. This is the formula, the molecular formula, correct? Or the molar formula of the compound. And within this compound here, you have 2.9610 power 24 atoms hydrogen. Now it asks you how much then the carbon. If you have this much of hydrogen, how much of the carbon? Well, you have to set up a ratio, correct? Between carbon and hydrogen. So the carbon to hydrogen is, so this is carbon here. Oh, sorry. This is carbon, and this is hydrogen. So I have 8 carbon and 8 hydrogen. And this will be then the same ratio. Y is the number of the atoms in carbon, and the number of hydrogen atoms is here. So solve it for Y. You get number of carbon atoms in C3H8 is this amount. And you have to watch the sig figs, of course. Correct? So, and you can see this one is exactly then is really holding the ratio constant 3:8. So this is the number of the atoms, Y number. If you divide the Y value with the value of hydrogen, you get 3:8, just to confirm it. Okay? Now, a sample that has 2.96 10 to the power 24 atoms. What is the total mass of the sample? Said, what is the total mass of the sample? Well, the total mass of the sample, we don't have anything, but we have the atoms of hydrogen, number of atoms of hydrogen, and number of atoms of carbon. We calculated here previously. This is the number, correct? So this is the number we calculate y. This is the hydrogen, and this is y is our carbon, correct? So now, what is the total mass of the sample? You do the same thing we did before. This is the hydrogen here, correct? Number of hydrogen atom given to me, and this is respond to how many carbons, how many hydrogen is 8. So this to this, correct? And if you divide this by this, you get number of the 3.70 10 power 23 molecules, correct, of C3H8. So you get the ratio of hydrogen atoms here, correct? That's the ratio here. You divide it by 8. That's the 8 here. And you get certain amount of molecules of C3H8, correct? So those are the molecules. And you divide these molecules by the Avogadro's number. So this is the molecules here. So the molecules cancels out. You get out of this mole ratio, correct? And if you look like this, this the mole ratio. That's the not mole ratio. That's the mole. You get the moles here, which is this value here. Then you have to multiply it by the molar mass of C3H8. So this value here is coming from C3H. Let me see here. C3H8. I mean this value here. So this value here. Yeah, trying to get this. Okay, so C3H8, the molar mass, 3 carbon multiplied by 12, that's about 36, plus hydrogen 8 is 1, so that's make 44. So the 44 is the molar mass of C3H8. You multiply it by, correct? You multiply this amount here. This is number of moles, correct? You get number of grams. So this is the molar mass, gram per mole, this mole. So the mole cancels with the moles out. You get number of grams. So now, this is very comprehensive coverage of empirical formula. So let's go together and look at this empirical formula. What is really empirical formula? Empirical formula is not like the normal structural formula. It is different from the normal molecular or condensed structure or Lewis dot structure. It's totally different. Empirical formula expresses the relative ratio of atoms within a compound or molecule. So it expresses the relative ratios of the atoms within a compound or molecule. So this ratio is held within the compound or molecule, held for the atomic level, for both atomic level as well as for the molar level. Let's look at this. I have magnesium chloride made of 1 atom of magnesium and 2 atoms of chlorine. This is atomic level. Or I can say, well, I have 1 mole of magnesium and I have in this 2 moles of chlorine atom. So I have molar level. So it's really a ratio of the atoms within the compound of molecule, which is really held for both molar and atomic levels, whether you consider this one number of atoms or number of moles. With the help of this empirical formula, we can determine the actual formula, the molecular formula of the molecule or compound. Correct? We can determine the actual molecular formula of a compound. So let's go and look. We have plenty of examples. So, and now ask ourselves, how in the world we calculate empirical formula from known mass percent? So we'll start with the mass percent is given to us. The first assumption here, so this is the first step here given to me. I have to convert this one here to assume that this mass percentage, 100%, is 100 grams. From there, I get what? I get number of grams. I take those number of grams, use their atomic masses, and then convert all those here to what? To number of what? Of moles. Then I calculate the ratio of the molar ratio between each element. Then I can get the empirical formula. We'll see a lot of examples. So you have a mass percentage. Let me repeat. You have a mass percentage. You assume this 100% is 100 grams. With the help of the atomic masses of each element, you convert those grams of the elements into number of moles. Then you make a ratio between these element number of moles, and then you can, out of this ratio, you can assign the empirical formula. Let's look at one of the examples. As I said, we have very comprehensive coverage of this empirical formula, and we'll go over several examples. The first one, the present composition of ammonia NH3. Well, how in the world I will know what's the composition of nitrogen and hydrogen inside ammonia NH3? Well, how much percentage nitrogen? How much the percentage of hydrogen? Well, it turns out, with the help of the atomic masses of each element, and make the ratio between those atomic masses to their overall molar mass of the whole molecule of ammonia, multiply by 100, I get what? I get the mass percentage of that element within this molecule, ammonia. So let's look at this. First, I have to determine the molar mass of the whole molecule of ammonia. 1 nitrogen is 14.0, 3 nitrogen is 1.0. I have molar mass of ammonia as a whole molecule is 17.0 gram. Now, nitrogen percentage, I have the atomic mass of nitrogen is 14, and I have only one of nitrogen. Divided by the whole molar mass multiplied by 100, give me this value. In ammonia, I have 3 hydrogens, so I have to put 3 here. 3 multiplied by the molar mass of the multiplied by the atomic mass of the hydrogen, 1.0 gram per mole, divided by the whole molar mass, multiplied by 100, I get this. So if you add those up, those will come to 100%, correct? They will add up to 100%. So that's an example. Let's go to the second example. The second example, I have the same example. This is thiosulfate. Thiosulfate is I have to look at how many sodium percentage, how many sulfur, how many oxygen. Well, first of all, you have to get the molar mass of the whole molecule, which is Na2H2O3. So we calculate the sulfur is 32, sodium is 23, oxygen is 16, and then you have to look 2 sodiums here, correct? 2 sodiums. Where is it? Yeah, here it is. 2 sodiums, and then 2 sulfur, and then 3 oxygens. You add up, the molar mass of the whole molecule is 1.58, 158.0 gram per mole. Now, you have the same thing we did in the previous example. You have to take the atomic mass number with the number of the atoms, of course, how many are present inside this molecule or compound, divided by the total, which is the whole molar mass of the whole molecule, multiplied by 100. So I have atomic mass is 23. How many sodium I have? I have 2 sodiums. Then I divide the whole thing by the molar mass of the whole molecule, multiplied by 100. I get this amount. Sulfur is the same thing. I have 2 sulfurs here, and then multiplied by the molar mass, atomic mass of sulfur, divided by the whole molar mass of the molecule. Here, oxygen, I have 3, and then the atomic mass of oxygen is 16.0, and then I take this one here, divide the whole thing by the molar mass of the whole molecule, multiply by 100, I get this. So if you add all these 3, it should add up to 100%. Now, let's look at the determination of percentage of H2O in copper sulfate pentahydrate. This is copper sulfate pentahydrate. This is very unique, and this is sometimes in the lab, in gravimetry. We have to know how many hydrate, how many molecules, how many grams or how many molecules of H2O attached to the salt, to the compound. So here we have the molecular formula is pentahydrate, 5 molecules of H2O is attached to copper sulfate. So now the question is, we have to determine the percentage of H2O. We need the percentage of H2O. Well, it turns out to be, your tuition will tell you, you have to split this one here. Let's split this one here by itself. 5 H2O, what's the molar mass of H2O? Is 18.0 gram per mole. And then you have to calculate the molar mass of copper sulfate, correct? And then you divide the H2O 5 by the whole molar mass of both combined. You see, first every one by itself, and then you have to add all the molar masses of H2O and copper sulfate together to get the molar mass of copper sulfate pentahydrate, and then you divide the molar mass of 5H2O divided by total molar mass of copper sulfate pentahydrate, including H2O, multiply by 100, that will give you the answer. Let's look at what's happening here. So first, we have to get the molar mass by itself, copper sulfate by itself, correct? I'm not going through this, and we know that this is just a sum, molar mass, a sum of the atomic masses of each individual element involved in the molecular compound. So it turns out to be this. H2O, we know that's 5. H2O, we know that's 18, because it's 16.0, that's oxygen. And 2 hydrogens, each one is 1.00, so that's just 2, that's 18. 18 multiplied by 5 is this. So this is H2O, and this is the copper sulfate. Add them up, so we have to add them up. We have to add them up here, and the total is what? 2.496 gram per mole. Now you take the 5 molecules of H2O, which is here, 5 molecules of H2O, you divide it by the whole molecule combined, copper sulfate pentahydrate, including the H2O, multiply by 100, that will give you the percentage of H2O inside copper sulfate pentahydrate. So the percentage is 36.1%, and the rest of the 100% is copper sulfate. Now let's look at the calculation of percent composition from the masses of the elements. An example, I have a sample that's 24.8 grams, and the sample is a gas or a gas state containing only carbon, oxygen, and chlorine. So this gas has 3 elements: carbon, oxygen, and chlorine. And then it's give you the amount of each of one. I have 3.0 grams of carbon, 4.0 grams of oxygen, and 17.801 gram of chlorine. what is the compound percentage composition? Well, as I said, it's just we have this composition percentage. Now I know that the total mass of the whole molecule is 24.8. That's the total, correct? Those are the totals here and here and here, the total mass. Then you have the individual element, 3.10 for carbon, 4.0 for oxygen, and 17.0. You divide the mass of each individual element by the mass of the total sample, multiply it by 100, you get the mass percentage of each element. So carbon is 3.0 gram divided by the total, 24.81 gram, multiply by 100, give you whatever the percentage is. Now let's look at how to calculate the empirical formula from the mass percent of each element at actual mass of each element. And this is really sometimes can be a little bit confusing for some students, but it's very easy. Just we say, remember, I can go back and just give you a hint for that. Let's go back and to the slides here. Yes, here. This is the slides. This slide. You get mass percentage of each element in 100%. So you assume this 100%, 100 grams. You divide each element, correct? Each element grams, divide by its what? By its atomic mass. To get what? To get the number of moles. And you then at the end divide by each number of moles. Correct? So let's go back and look into this. So we have an example here. We have chloroform is made of 10.06 carbon, 0.85 hydrogen, and 89.09 chlorine. So those are making up. So what's the first step? Is assuming that I have 100%. So I have 10.06 gram carbon, 0.85 gram hydrogen, and 89.09 gram chlorine, correct? So let's go and look. So exactly, that's what's happened. So I assume that the sample is 100 grams, correspond to 100%. And those are given to me the percentage converted into grams. The next is I use the atomic masses to divide, correct? So divide the whole thing to get the moles. So now the 10 grams carbon divided by the atomic mass, 1 gram per mole, of course, I get this number of moles. For hydrogen, here, divide by its molar mass, I get this number of moles. For chlorine, number of grams, I divide by atomic mass, I get this number of moles. This is until now, the steps are straightforward, no problem. Now to get the empirical formula, I have to divide by the least, I make a ratio by the least number. So the least number, it looks to me, is this one here. So divide the whole thing by this number. I get this one about 1, this one about 2, correct? No, sorry, this one about 1, almost. And this one here about, I think about 3. Yeah, so you can, about 3. So 113. So 113. So carbon is 1, hydrogen is 1, and chlorine is 3. So this will be then our empirical formula, and that's really correct here. Look at this. This is the empirical formula of C1H1Cl3. This is for the chloroform, correct? So that's how we can get the molecular formula for empirical formula for chloroform. Now let's do another example. We have 32 grams of the whole thing, correct? The compound, the whole thing here has phosphorus is 0.72 grams and chlorine is 2.50 grams. What is the empirical formula? Here there is no percentage, correct? Now the whole idea of the empirical formula is to make the ratio among the moles. So our goal in empirical formula to get number of moles of each element by itself, and then compare those number of moles to them by themselves, and divide by the smallest number of moles to get the ratio of the moles within the molecule, of these elements within the molecule. So I have the whole total is 3.2 grams, correct? The whole sample gram is 3.2 grams, correct? And it has 0.72 gram of phosphorus. So if you look at this, this is the amount of phosphorus, this is the amount of, and this is amount of chlorine. Now the atomic mass of phosphorus, again, we have to get the moles. That's the whole idea. So I divided by the number of moles of the molar of the atomic mass of phosphorus, which is 31.0, and the chlorine, I take whatever the amount of chlorine divided by its atomic mass to get number of moles. So when I look at this number of moles, again, I have to everything in 3 sig figs, because this is all this 3 sig figs, so my answer 3 sig figs. So, and if you look here, 0.235 and 0.074, you divide this one by this is the least, correct? And it looks like if this one will be 1, and the other one will be 3. And if you look at this, divide by the least one is 1. Here it is. That's what I did. This is 1. And this one here is, take this one divided by its least, you get 2.99, which is really 3. And this is the empirical formula of this compound, P1Cl3. So let's go further. Now, the most challenging part of the whole empirical formula for most of the students, as I know through the years, is in the 2-3 examples here. This is the last topic of the empirical formula, which is the most difficult part for the students. So let's look at this. We have to calculate the molecular formula, correct, for a compound by using empirical formula. With the help of the empirical formula, how I get to know the molecular formula, correct? So what is the molecular formula if I have calculated the empirical formula? Well, here's the form. Here it is the formula here we have to follow. And as I said, the empirical formula is the smallest whole ratio, mole ratio of the elements within a compound or molecule, correct? The molecular formula is the actual one, the real one, not the smallest number, but the actual number of the atoms or number of moles of each element within a compound or molecule. So you can see the difference. The empirical formula is the reduced, or the least number of the ratio of the least among the least number of moles within of the elements within the molecule. But the molecular formula, there is the actual number of the moles or atoms of each element within the compound of molecule. But back to this formula here, if I have the molecular mass, correct, in AMU, if you recall, molar mass is given a unit of gram per mole, or AMU, if you recall back in Survey of Chemistry 1, Introductory Chemistry, AMU stands for atomic mass unit, atomic A, mass M, U unit, atomic mass unit, or gram per mole. They are 1 gram per mole equal 1 AMU, correct? So if I divide the molar mass of the whole molecule by the molar mass of just the empirical formula, I will get N formula units per molecule. And this, with the help of N, then I can, this is my final structure. How can I get the structure? Where it turns out to be the molecular, the molar mass of the molecular formula will equal N multiplied by the empirical formula mass. And as I said, let's look, we have a couple examples here. And as I said, this is the most difficult part of the empirical formula to follow, okay? And you can always go back and look what the difference. This is the empirical formula, the least ratio, mole ratio of the elements within the molecule. Molecular formula is the true actual ratio, correct? The true actual ratio. So let's look at the example here. It says the empirical formula of hexane, C3H7. So hexane is the empirical formula of it is C3H7. So the molecular weight, this is the whole. This is what? Total, the whole thing. This is the total. Is 86.2 AMU or gram per mole, correct? AMU or gram per mole. What is the molecular formula of hexane? We know this is hexane is not. Hex means 6, so we have to have what? Carbon. Carbon has to be 6 because hexane is an alkane, if you recall. Hexane. And if I can tell you, I can give you an advance, is C6H14, correct? That's hexane from Survey of Chemistry 2, if you recall. But let's calculate. I gave you, or the example is giving us, the molar mass of the whole molecule, of the whole compound hexane is 86.2, and give you the empirical formula, and tell you what is the molecular formula, the real, actual rate, expressing the actual ratio of the elements within the molecule hexane. So what we will do, we have to get the molar mass of the empirical formula. This is the first step. This is the first step. We have C3H7. That's the empirical formula. What's the molar mass? I have 3 carbon and 7 hydrogen. Carbon is 12.0 gram per mole multiplied by 3, and hydrogen is 1.0 multiplied by 7 of hydrogen. This is 43 AMU or gram per mole, correct? Then I take the whole molar mass. I take the total whole molar mass divided by 4,3, correct? It came out the N, remember? 2. If you just recall what N is formula units molecule. Ratio between the molar mass, N is the ratio between the molar mass of the whole molecule divided by the molar mass of the empirical formula. So if you divide, you get 2. So now I need to get the molecular formula. The molecular formula is 2 multiplied by the empirical formula, which is C6H14, and that's what we really know before. So this is hexane. That's the real formula, molecular formula of hexane. Let's look at another example. The compound dioxane contains only carbon, hydrogen, and oxygen. When this amount of dioxane, this is the whole sample, here it is, the whole sample of dioxane is burned in 1.9 gram dioxide and 0.7 gram of H2O are formed. In another experiment, it was determined that 6.04 10 power 10 minus 3 mole dioxane weighs 0.532 grams. What is the molecular formula of dioxane? Well, look at this. It gives you that you have carbon, oxygen, correct, and hydrogen. Now for the carbon, you get the elemental analysis to determine carbon. You get this one oxidized, and you get carbon dioxide. So it tells you that the amount of carbon the amount of the carbon, correct? If you look at this, amount of the carbon here, it's 1.9 grams, correct? That's here. If you look at this, carbon dioxide, 1 grams. You divide it by the molar mass of carbon dioxide, which is 44, and then you look at yourself. You look at the atoms within the molecule. So I have 1 mole of carbon dioxide has 1 mole of carbon here, correct? And it has in 1 mole of what? CO2. So this here, I did what? I got my amount of carbon inside dioxane molecule. So I did the same thing for H2O. H2O is recovered to be 0.78, correct? Divided by the molar mass of H2O, 18.0 grams. I have 2 moles of hydrogen in 1 mole of H2O, correct? And then transfer this one here, atomic to the atomic mass of hydrogen is 1 gram per mole. So I get this amount of grams, correct? Now I get hydrogen and carbon, and I have the total here is, and the total here is, the total is 0.95. This is the total here, dioxane, correct? So this is the total of dioxane here, minus the number of carbon, grams, minus the number of hydrogen, grams. I get number of oxygen. So now I have those three. I have what? I have those three. Now I have all those three, the whole thing. Now I have to convert those grams into what? Into moles, correct? I have to convert those into what? Into moles. So I take whatever this 0.52 grams of carbon, divide by 12, this number of moles, I get this number of moles. Hydrogen, take the hydrogen, amount of hydrogen, divide by the molar atomic mass of hydrogen, I get number of moles of hydrogen. And the same thing with oxygen, this amount of oxygen, grams, divided by its molar mass, I get this amount of moles of oxygen. So now let's go for the next one. Here it is. I have the empirical formula is, let me see here. The empirical formula is carbon is 0.043 moles, hydrogen is 0.087, and oxygen is 0.022. So let me go back. So if you look at this one here, if you look at those values here, the least number is oxygen, 0.022. You divide by the least number here, go back. So here it is, oxygen is 0.022, hydrogen is 0.87, and carbon is 0.043. You divide by the least number, you get oxygen is 1, carbon is 2, and hydrogen is 4. This is the empirical formula of the dioxane, correct? Now, I need, is given to me, correct? Is given to me, that's the molecular weight of oxygen, gram per mole. So it's given to me the number of grams, correct? And the number of moles of dioxane. So the amount of the molar mass of the dioxane is this amount, 88 grams. And that's, if you want to ask yourself from where, that's from the sample. From the sample. So you have, this is dioxane weight, this one here, and this is small. So you divide this grams here, okay, divide this grams by this moles, you get what? You get the molar mass of the whole molecule dioxane, correct? So, and that's what we have here. That's what we have here. We divided this amount here by this number of grams by this moles. I get the molar mass of the whole molecule here. So now I know the molar mass of the whole molecule. I go and make myself the old stuff here, correct? The formula, the molar mass of the whole molecule dioxane divided by the empirical formula molar mass. I have to calculate the molar mass of the empirical formula, which is, we say the empirical formula is, this one is the empirical formula, correct? 2 C carbon, 2 H4O oxygen. So I have 2 carbons, here it is, plus 4 hydrogens, plus 1 oxygen. You add them up, you get 44. So you divide 88, that's the total for the whole molecule, molar mass, divided by the molar mass of the empirical formula, which is here, correct? So then you get 44, 88. So the N, which is the formula here, N is 2. That's the ratio of the whole molar mass, correct? By the empirical formula, molar mass will give you, again, let me just repeat this one here, we have it. Here it is. We will be repeating this. It's very important to memorize at least this, or just get familiar with this. Molar mass of the whole molecule divided by the molar mass of the empirical formula will give you ratio, will give you N, which was called formula units per molecule, correct? So now you have this, here it is. Now we are molecular dioxane, 2 multiplied by the the molecular formula now, multiplied by empirical formula. C multiplied by will be 4, hydrogen 4 will be 8, and oxygen 1 will be 2. So this is the molecular formula of dioxane. So we'll be looking at one example, one more. The compound of ethylene glycol is often used as antifreeze. It contains, now I'll give you the percentage, carbon is this, and hydrogen is this, and the rest is oxygen, so you have to subtract them from the percentage. The molecular weight of the ethylene glycol, that's the whole molecule here, that's the whole molecule. What is the molecular formula of ethylene? Molecular formula means the whole actual rate of the whole molecule, of the whole elements within the molecule. So that's the actual one, not the empirical one, but the actual one. Well, assume this is because you have the percentage. First of all, you have to get the oxygen. Here it is. Oxygen is assume the 100% is 100 grams. Oxygen is 100 gram minus carbon minus hydrogen came up to be 51.55 grams. So you assume the percentage into grams, 100% 100 grams. Now we are converting those grams into moles. You divide by each individual atomic mass of each element. So this is amount of carbon divided by its atomic mass. You get this number of moles. This is the amount of hydrogen, grams, divided by atomic mass, you get this amount of hydrogen, mole-wise. This is the grams of oxygen, divided by its, this one has to be 16, sorry, this, yeah, and this is correct, by the way, so this has to be 16. Yeah, this one has to be 16, yeah, sorry, I apologize. This one has to be 6, yeah. Yeah, 16. So you get 3 number of moles of carbon, hydrogen, and oxygen, correct? Which one the least? Well, it turns out to be carbon, correct? Number of moles with oxygen are equal, but hydrogen is more, correct? So it looks like carbon is 1, oxygen is 1, and hydrogen will be around maybe 3. Maybe 3, yeah. So let's look at this. So it turns out to be hydrogen is 3. Here it is, guys. Hydrogen is 3, carbon is 1, oxygen is 1. When we divide divide among the ratio, let's look at the ratio here. This one will be 1. This one will be 3. This will be 1. And that's what we have. That's what we have here. So the molar mass of the whole molecule with the empirical formula. The empirical molar mass formula is 1 carbon, correct, plus 3 hydrogens plus 1 oxygen makes 31.03. So you divide 62. 62 came from the question here. This is 62. Here it is. Here it is. Here it is. This is the molar mass given to us. So you divided, that's the whole molecule given to us, divided by the empirical formula we calculated, correct? So the whole thing is 2. So now you multiply the molecular formula CH3O by 2, you get 2 carbons and 6 hydrogens and 2 oxygen. And this is the molecular formula using empirical formula. Thank you very much, and I will continue in the second part. Thank you.